Hi all, today we will learn the frame pointer attack and another trick to exploit the buffer overflow vulnerability. This attack can change the control flow of the program even when you cannot overwrite the return address, but can overwrite the saved EBP, the frame pointer. That's why it is called a frame pointer attack. Before start, please note that the week 1 due has been passed, so you can get only the 50% points of the flag for the flags you submit until from now on and until April 20th. And for week 2 challenges, the due date is on April 20th, and the same 50% discount applied to the late submission if you submit it from April 20th to April 27th. And let's start with covering the recall the buffer overflow attack example. In the stack diagram on the right side, we assume that we have a 4-byte buffer in here, and if you fill the longer string than 4 bytes, such as 1111 A B B B B C C C and DDD and getter shell, the address of the getter shell, then it will overwrite it as all the local variables and also for the return address as the address of the getter shell. Then the program returns to not to the original return address, but returns to the overwritten return address, the getter shell function. That's the basic buffer overflow attack. And to understand the frame pointer attack more correctly, let's as a prerequisite, let's take a look at the function epilogue and how stack changes in detail. We have the following 4 instructions at the end of the function, and then the first instruction is add 0x54 to ESP. This the 0x54 is 84 in the decimal value. It is taken because the exact value has been taken at the function prologue, because it subtract the 54 from ESP, so it will add back at the epilogue. So that value you can see at the function prologue has been taken. Yeah, and then what it does is just it will restore the ESP value before it was subtracted by the function prologue, and then pop ESI, pop EBP, and then the ESP points to the return address where the return address has been stored, and then return. Then it will run the getter shell function. So an important point here is that the first instruction restores the ESP, and then third instruction restores EBP. But right now we have overwritten the saved EBP value to the 64, 64, 64, 64 we fill as a DDDD, so it will have an invalid value, but we didn't care about that because we just directly run a getter shell function to get the privilege and read the flag. And these operations, restoring ESP and EBP, happens a lot when the function returns. And at this point, let me introduce a new set of instructions that does these 2 operations at once. For example, add ASP and pop EBP at once. And the instruction is the leave instruction. Yeah. And what it does is you can interpret the leave instruction as running the set ESP to the value of the EBP and then popping the EBP like this. Set the value of ESP to be EBP and then pop EBP. So the leave instruction will first set the ESP to be the value of the EBP like this. So ESP will move up where the EBP points to, and then pop EBP, so it will restore the value of EBP to the previous value, save the EBP value, and then it will go 1 up because the instruction internally runs the pop, and then function returns, so it will return to the original return address. We just learned about how function epilogue works with either the add ESP, pop EBP, or leave return. And then from now on, let's take a look at the frame pointer attack. To start with that, let's delve into what Ebp Register does. And if we are not running the function prologue or function epilogue that changes the value of the EBP and ESP, then in a regular time, in the most of the regular time, ESP should always point to the end of the stack frame, and then the EBP should point to the start of the function's stack frame. So you can think it as the stack function's stack frame starts with the EBP and ends with the ESP, and then the EBP should always have the bigger address than the ESP. And that's why leave return pair works as it will move ESP to EBP, then pop EBP will be restoring the saved EBP, so ESP will be here, and then EBP will move up there for the saved EBP, and then pop the return address. And then next is about the frame pointer attack. What if the buffer overflow vulnerability lets the attacker may overwrite the saved EBP but not the return address? For example, attacker can overwrite the saved EBP, but the length that the attacker can overwrite ends at here, then attacker cannot overwrite the return address to the getShell function. In such a case, can we still run getShell function? The answer is yes, and this is possible with the running this function epilogue for 2 times. The 2 times is important here, but having just a single leave and return will not let us change the return address. And I will show you that with the diagram example. So the leave instruction will first move ESP to EBP, something like this, and then it will pop EBP. So the value of EBP will be this value, 64, 64, 64, 64, and then ESP will move 1 up. And then now ESP points to the original return address. And then the program returns with the return instruction, then it will return to the original return address. But it seems like it does not have any kind of problem because it will return to the original return address, but this is problematic if the program returns twice. So in the buffer overflow level 5 challenge, the program's call chain is it will start from the main function. The main function calls the run function, and then the run function calls the receive input. So it has like the depth 2 of the call chain, and then right now we just take a look at how the program runs in the receive input. The function contains the vulnerability, and then there will be one leave return here, and then another leave return here. So in this example, we just ran the leave return in the receive input function with this kind of the attack vector overriding the saved EBP as a 64, 64, 64, 64 as an example. And then there will be another pair of leave return in the run function. Then what will happen if we run leave return twice, not just once? So if we run the leave return once, then it will return to the original return address. We didn't see any kind of problem. Then what will happen if it runs twice. So let's see the example. There will be another leave return in the run function. It will first move ESP to the position of the EBP. So it runs like this. ESP will be 64, 64, 64, 64. And then pop EBP is the next instruction. So it tries to pop the value of EBP from the address 64, 64, 64, 64. And internally, it will work something like this. So because pop EBP will get the value inside the ESP to EBP and then add the ESP plus 4. However, right now, the address where ESP points to is 64, 64, 64, 64, which is an invalid address. So it will fail. And to check how it runs, you can use GDB to trace it. And how you can do is like you can first set the breakpoint at the leave of the receive input, which is a receive input plus 32. And then if you continue to run it, so it will break right at the leave instruction of the receive input. And you can check the value of the ESP and EVP. So right now ESP points to FFFF D3E0, and then EVP points to D468. So EVP has a bigger value than ESP. And then we can continue to run it. So not the continue, actually. If you run the next instruction, then it will stop at the return instruction. And then we can check how the value has been changed. So because we put the saved EVP as a DVDD 64, 64, 64, 64, after running the leave instruction, the value of the EVP will be 64, 64, 64, 64. And then the value of ESP has been changed to the previous EVP plus 4. So previous EVP value is FFFF D468, D468. And then now the ESP points to D46C, which is D plus 4 of the D468. So the leave instruction runs as we know about we have seen the how it works in the diagram. And then let's continue to run to the leave instruction of the run function. We can set the breakpoint and then continue the execution up to that point. Then at here, the value of the EVP is still 64, 64, 64, 64. We haven't changed that. And then the value of the ESP is changed a little bit. So FFFF D470. It doesn't matter. And then now it will continue to run the leave instruction, but it will generate the segmentation fault at the address 64, 64, 64, 64. The reason is internally the leave instruction tried to move ESP to EBP, so ESP will change to the value of the EBP, which is 64, 64, 64, 64, and then tries to pop the value of the EBP from this address. But this address is an invalid address, so that's why it generates the segmentation fault. In this example, although the debugger does not show the value of the ESP correctly here, because it is written as a leave instruction, so the CPU internally generates the fault. But the meaning of the instruction internally, the CPU runs these two pairs of the instructions when we run the leave instruction, so it will generate the segmentation fault when it tries to change the value of the EVP to this and read that. Now we understood why simply overriding the frame pointer to the non-address does not work. Excuse me. And let's think about how we can exploit this case. So now we know that we can change the value of the saved EBP, which is the EBP of the upper level function. Yeah. And then in the upper level function, run function, yeah, important thing here is that EBP plus 4 should always store the return address. For example, let's go to this, this example. Yeah. So in a regular execution right before the running the function epilogue, yeah, we will see that the EBP plus 4 should always store the return address. That's the important thing. And then what we will do is, like, by controlling the saved EBP, yeah, we will make the EBP to points to the fake stack frame, and then that value EBP plus 4 should store the return address. Then the code will return to the return address that we want to control. Maybe you cannot get how it works, so let's take a look at the example with the diagram. Suppose we have the stack frame like this. We have only like a 4-byte buffer with the sum of the local variables, and then the saved EBP at here, and then return address at here. And suppose our original EBP value is at the FFFFD540, so this address is the FFFFD540, and then the buffer address at here is FFFFD530. And then we will put the address of the buffer as the overriding value of the saved EBP, like this. This address will be overwrite, will be exactly the address of the buffer start. And then let's try to run the function epilogue in this setup. It will first move ESP up to EBP, and then pop EBP. Then now pop EBP will move ESP plus 4, and then EBP will be changed to this value. So then now ESP points to the where return address is stored, and then the EBP will point to the start of the buffer in the stack, because we changed the saved EBP as the address of the start of the buffer. And then it returns to the original return address. So it does not have any problem on the control of the program, but the problem is that the now EBP does not point to the end of the stack. It will point to the somewhere below the ESP, which is weird. And then that conforms the first step of the frame pointer attack. You need to change the where EBP points to somewhere below, or somewhere you can control your input. And then in the second leave and return in the run function, it will move ESP. It should move ESP up to EBP, but right now it will move ESP down to EBP. Yeah. And then run pop EBP, which means ESP will be plus 4, and then pop EBP means like it will get this value as the value of the EBP. So the now EBP value will be 31313131, and then ESP points to where 61616161 is stored, and then return, where it will returns to. So it returns to 61616161. But this value we can control. So then where do you want to put the address of the Gato shell? Maybe here. Then it will return to not the 61616161, but it will return to the address of the get shell. Then let's take a look at the final example diagram. So how you can set it is that first you need to get the address of the buffer, and then put the address of the buffer as a saved EBP. So to do that, you need to also calculate the distance between the saved EBP and the start of the buffer. You can fill all the local variables and other parts of the stack with some of the dummy values, and then put the address of the buffer as a saved EBP. But at the same time, you can put the address of the get shell at the +4 of the start of the buffer. And then when we run a first leave and return, it will move ESP to EBP like this, and then pop EBP. So EBP will point to the start of the buffer, and then ESP will point to the original return address, and then return. And then it will have the second return in the run function. So it will move ESP down to EBP, which is weird, and then pop EBP. So EBP will point to the 31313131, but ESP will point to the buffer start +4. And because we put the address of the function get shell here, then it will return to the get shell function. So in the frame pointer attack, you can control the return address of the upper level function by overriding the saved EBP. And a simple attack formula would be set the saved EBP as the SAM address of your input. Right now we use that as like a start of the buffer, but it does not have to be the start of the buffer. Any address that you can write some of the value, you can use that. And at the same time, because it will run pop EBP, so it will actually set the ESP as a that saved EBP and at the second return, and it will run pop EBP internally. So we need to put the return address as that saved EBP value +4, because there is a pop EBP instruction. So ESP will be the saved EBP, and pop EBP will increase address 4 to the ESP, so the return address should be at the overwritten value +4. And I hope you understand how frame pointer attack works with the toReturn with the diagrams in this slide. And if you did not, then please follow the diagram again and again, and to actually exploit the vulnerability with the challenge. And if you still cannot understand how it works, please try to draw the diagram, stack diagram, like what we did in this slide, and try to practice by your own and how the ESP and EBP values changes. And you can also trace that using GDB with the exact address value. And for the next few slides, I put some useful commands for Pawn tools, so please refer to these slides and use these commands for your convenience. And as the final remark, the due date of the week 2 challenges are on April 20th, so please do not forget the due date and finish them on time. Thank you, and this is the end of the lecture 5.